Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So this is sort of covering some recent work with a bunch of people, Amit, who's in the audience, Andrew, Malcolm Itzmacher, Justin, and Kevin, who's around as well. So I'm going to sort of start by talking a bit about streams, and this is a topic that was touched on yesterday by Sudipto and will be also touched on again by several talks in the afternoon. So, one of the first takes on how to deal with big data, one of the valid approaches to say, can we sort of process large amounts of data with a single or constant number of passes over that data to keep some small summary information that lets us answer some interesting questions. This came out of data coming from networks, but more generally we can sort of think of streaming over many different kinds of data. And this has certainly been very productive in terms of algorithms, in terms of sort of what we can do, and so we have a pretty good understanding of the kind of things that we can do in streaming. There's still a lot of active questions around what we can do. The main issue in streaming is that because you're keeping a relatively small amount of information relative to the full size of the data, then typically we're working in the domain of approximation, approximate answers, probabilistic guarantees. And so the kind of parameters that we're interested in are things like, well, what's the space accuracy trade-off? How much time does it take to process each update? How accurate do our answers get? What's our probability of error, and so on. So what do we know? A lot of sort of fairly fundamental sort of basic analytics kind of questions we can answer very efficiently in the stream model. So the most basic question is, how many different things have I seen? If I've seen a huge number of different items streaming past, actually how many distinct items have I seen? And can I then sort of pose cardinality questions about subsets of items? We can also pull out sort of the peaks, the significant entries in these distributions. We can look at information theoretic quantities like entropy. So we have quite a few primitives that we can then build on to do more advanced things. But at the same time, streaming is kind of hamstrung by the fact that actually a lot of very basic questions are hard in this model. And what we mean by hardness here means that to actually give any accurate answer to these questions, we need to devote an amount of space that's essentially proportional to the size of the input. So in other words, this ideal of having a small space summary of a large amount of input sort of goes out the window. And what are the kind of canonical hard problems here? Something as basic as saying, well, I've seen billions of items stream past. Did I see an item of type X? Just that sort of simple indexing question we know needs us to devote a large amount of space. More generally, things like in a product between two vectors, which comes up in any kind of similarity computation, again, is something that's hard to do accurately. We can get some weak approximations to this. And Amit will talk this afternoon about stronger lower bounds for various problems via communication complexity and information complexity arguments. So this is sort of a bit disappointing because it says that while there's a bunch of stuff that we can do fully in this streaming model, there's enough hard things that we can't really think about doing general purpose computations here. So what I'm going to talk about today is sort of saying, well, can we still take some of the good parts of streaming and sort of combine them with a more powerful computational setting? And it comes up in the following sense. All right, so if there's lots of things that I can't compute fully in the streaming model, well then let's just go to someone else who's got lots more resources, who can store the full data, get them to do the computation for us, and let them do the work. And then we sort of hit on this sort of fundamental question. Well, if someone else is doing the work for us, some outsourced entity is promising that they're doing the computation and giving us back an answer, how do we know that they're actually telling us the right answer? How do we know that they've actually done the work that we asked them to correctly, rather than just made up some answer and said that that's what they've done? So what we're interested here is sort of looking at this multi-party situation where we have what someone we're going to call helper or prover who's actually going to go off and do the work. And we think of ourselves as sort of the weaker streaming entity who wants to verify, is this answer correct? And in particular, can we do that in a way where verifying the answer is a lot less effort than computing the answer? So this has some deep theoretical connections. It connects, I can sort of throw out terms like communication complexity, Arthur Merlin model, streaming versions, algebraization, all these things. But I'm also going to try and convince, at least towards the end of the talk, that there's some practical application of this, that this is something that we can actually implement and make work. And why we want to do this, I've sort of hinted generally this kind of cloud computing scenario where we throw our computation to the cloud and then get some answers back. We'd like to know that. Sort of in microcosm, you can get the same situation where within a particular system you have various components where you don't necessarily where you're sort of outsourcing effort to those components, and again you'd like to cross-check. So this is a situation just where you can also think of this sort of as a lightweight checksum for computation to try and see, has there just been an error? When you're dealing with huge amounts of data, the chance of discrete errors, cosmic rays disrupting your CPU becomes sufficiently large that maybe you want these kind of checks on the correctness of a computation. So here's sort of the first setting. Sort of trying to formalize this a little bit and look at just a sort of a simple one-round approach to this. So here what we're thinking of is, again, we have our sort of our weak little verifier, our strong prover helper, who is they're both seeing the same input, which we can think of as streaming past, and the helper or prover is going to provide their proof to the verifier of a particular computation. So what are the properties that we want here? Essentially, the main properties sort of down here are that we want the probability of the verifier accepting a wrong answer should be small, and that there should be some proof, some help string that the prover can provide that with high probability convinces the verifier to accept the correct answer. And again, what are the parameters here? The parameters are essentially what it turns down to is it boils to two sort of space-related parameters. What is the size of this proof, this help cost h, and what is the amount of memory that the verifier needs to perform their checks? So let me sort of work through one fairly specific computation and show how you can actually construct a protocol in this setting that has the desired properties. So we're going to focus on this problem of frequency moments. People that have seen streaming before know that streaming people love frequency moments. It seems like sort of a canonical computation, and the reason for that is actually that there's sort of something fundamental about this problem, and it actually upper bounds techniques that work for this problem tend to generalize and give interesting algorithms for a whole bunch of other problems. So what's this problem? The problem is that we see a sequence of items in this long high-dimensional stream. So each item is drawn from some very large universe of possibilities. We'll let Wi denote the frequency of item I, and what we want is this just simple mathematical quantity, sum over all items of the frequency of the ith item raised to the power k. This is difficult because the items are coming distributed, so we can't easily directly compute Wi from the stream. There's so many different items, we can't keep track of them. So to compute this exactly, the natural thing is just to keep a counter for every different item type and keep track of them, and then at the end of the stream do this computation. And it's something people have looked at. It's something that's relatively hard to approximate for moderate values of this parameter k as well. So what are the kind of results that we get here? It's a little bit hard to sort of parse completely off here, but what it's basically saying is that actually we have a nice trade-off that says for any setting of these two parameters h and v, where h is sort of the size of the proof and v is the space of the verifier, so long as the product of those two terms is larger than n, the domain from which the items are drawn, then we have a protocol where essentially the size of the proof scales linearly with this parameter h, and the space of the verifier scales linearly with this parameter v. So to make this concrete, what this is saying is that with space that looks roughly like square root of the size of the input for the verifier, and a proof of comparable size, also square root the size of the input, we can compute exactly this quantity in this sort of proof setting. And in some sense that's surprising. Again, it's saying that this huge thing, then we have two resources which are both only square root the size of this huge input. So what do we do? This isn't, here we're actually going to sort of pull out some sort of algorithmic technique that turns out to sort of solve this problem. So what we do is we start thinking about input as sort of a long array. So think of this as the array of item frequencies, right? The first item has frequency 3, second item has frequency 7, third item has frequency 1, and so on. So the first thing we're going to do is sort of think about how do we lay this out. We're going to reconfigure it in this sort of array as an H by V array. So we have the sort of the full domain. We know the size of that domain. We can reformat that array that into this array. And then here's sort of the trickiness here. We can think of that array of values as defining the values of a polynomial, right? That there is some polynomial that if I evaluate it at this location, sort of 1, 1, will give me 3. There's the same polynomial if I evaluate it at this position, 1, 2, will give me 7. At this position, will give me 0, and so on, right? That's just a basic fact. If I have a sufficiently high degree polynomial, I can define one that agrees with this way. And then the trick is we're going to use this polynomial essentially sort of like an error-correcting code, like a checksum, because we're going to take that polynomial that agrees with our input fully and pick somewhere outside the domain of the input to evaluate that. Right? So in particular, we're going to pick some random R, which the verifier takes, which is hidden secret from the prover, and evaluate this extension of the input at this random location. So think about sort of setting up some sort of set of values away. Here's sort of the region where the input is defined. Sort of extrapolate out that same polynomial out somewhere else and evaluate it down there. And this is called the low degree extension of the input evaluated at those locations. And then the protocol has the following form, that the prover is going to send some information which is meant to help us do this particular computation. So what they're going to do is essentially do sort of a partial aggregation. They're going to send a polynomial. So here we had a polynomial in x and y that was sort of giving us this full range of values. The prover is going to send us a polynomial only in x that's basically a partial aggregation of the function that we want. Right? It's aggregated by summing over j values of this sort of partial entries of the function for a particular x. So for one value of x, it's essentially the summation of one row of the entries in one row raised to the power j. For a different value of x, it's the corresponding summation of values raised to the power j for that row. So why is this a good thing? Well, essentially because of the way we've constructed this check for the verifier can say, well, if this polynomial that the prover has sent me is as is claimed, then I can evaluate that sent polynomial at my secret random location R. So I can evaluate what should be the sum of entries raised to the power k for this row R. And then the verifier has got, because of their evaluation of this extension of the input, the necessary values to then compare and check. Right? So based on the information that the verifier has kept, they can see if at the secret location R, their calculation agrees with what's given by the prover. And if they agree, essentially we can argue that the chance of, if what the prover sent was not honest, was not as it was claimed, then the chance of that agreement happening is very small. So we're pretty convinced that actually this is the right polynomial. Okay. So there's some amount of reasoning and algebra behind this, but the basic idea is to say, we come up with this interesting sort of algebraic check on the honesty of this computation. So sort of where's the streaming part of this? The streaming part of this, where this gives us most of our power, is in the fact that the verifier can do this evaluation. Right? We're asking the verifier to sort of think of reformulating the input, restructuring it, interpreting it as a polynomial, extrapolating it to a random location, and evaluating it there. And sort of what's maybe surprising is that all of that can be done in a streaming setting, because that actually turns out to be a completely linear operation. So yesterday's Sudipto was extolling the virtues of linear computations as being very powerful tools, being very flexible, working in streaming, also sort of trivially working in distributed MapReduce settings. So what's vital here is the fact that the verifier can do this incremental computation of the evaluation of the low degree extension at the random location incrementally as that function, as that input is defined by the stream. And in some sense, the reason for that is fairly simple, that if you look at what that computation is, then every update that is received in the input, you can think of as being an impulse, right? It's you're adding on to that array the input, an additional array that's 1 at the location of the update and 0 everywhere else. And then what we want to do is, what we can say is that our evaluation of the extension of the input is equal to our evaluation of our current evaluation of the extension of the input, plus our evaluation of the extension of that impulse polynomial defined by the location of the update AB, evaluated at the relevant locations. And what this turns out is that this sort of update polynomial, this P sub AB, is, again, it looks a little bit off-putting the first time you see it, but it's something very simple. It's called a Lagrange polynomial. And moreover, it's just sort of a multiplication of things that we can do in the field, so we can evaluate it very efficiently in small space incrementally. And if we really want to engineer this, we can start doing tricks like pre-computing partial values, lookup tables that make the computation of this update very simple. So when you put all these pieces together, this actually says that we have a nice protocol in one round for checking this particular computation. And then why is something like second frequency moments of interest to us? Well, I sort of said it applies to a bunch of other things. So sort of directly, I said that in the traditional streaming model, something like inner product is hard. Once we have a primitive like this, inner product follows immediately. Right? So we've shifted the model, and in this model, we can exactly compute inner products in this verified way. Here's sort of the way you do it using this primitive. You just observe that the inner product between x and y can be expressed in terms of the second frequency moment of combinations of x and y. You can more directly just adapt that protocol that I showed in terms of extrapolation of the input to verify that directly. If you don't want the exact answer, you can sort of improve the cost of the trade-off by looking at the approximate, say, second frequency moment, by taking approximate methods and sort of plugging them into this framework. And you can do other things. You can sort of approximate, say, the maximal value, the maximum weight, the maximum frequency of any item, based on connecting that to approximations of sort of larger and larger values of the frequency moment. So once you have this, there's a lot of sort of simple things you can do. And as we go on, I'll talk about even more general computations. So what that says is that just with a single round of proof, essentially where the prover can provide the proof, don't need any direct interaction with the verifier, they can just sort of publish that polynomial that they need to provide and then go offline, then we have a pretty good set of results. We have essentially, in that particular example of the trade-off I gave, you have sort of square root n space for the verifier, square root n size of that polynomial proof that the prover has to provide. Well, it turns out that if we can tolerate more interaction between these two parties, you can exponentially improve both those resources. So now think of, rather than just a single proof being sent from the prover to the verifier, think of sort of multiple rounds of interaction between the two players. where the prover sort of makes some initial statement, the verifier comes back with some, say, think of it like a challenge, and we go back and forth until the verifier is satisfied. How does that work? Essentially, it takes the previous idea and sort of generalizes it from one round to multiple rounds. And if you're familiar with interactive proofs, you'll sort of see echoes of the kind of sum check protocols that occur there. Similar kind of idea. So before we did this sort of layout of the data in a rectangle, now you can think of this as laying out the data in a hypercube, but actually it's probably easier to visualize as laying it out at the leaves of a binary tree. And a similar sort of idea that the verifier is going to pick sort of a location in this hypercube, this generalization of the hypercube, where instead of binary coordinates, they're allowed to pick sort of arbitrary integer coordinates and extend the function out into that space and evaluate a particular function, evaluate essentially the input extrapolated out to that random location and use that as their check. Then what's the interaction going to look like? The interaction is going to sort of proceed down this sort of binary tree structure. The prover is going to make essentially an initial claim that relates sort of directly to the overall output. Then in each round, you can think of the verifier's secret location as being sort of a coordinate in this d-dimensional space. In each round, the verifier divulges one of those coordinates and then forces the verifier to incorporate that into their computation. So essentially, in the first round, the prover makes a claim about sort of the whole input. And then in the first round, the verifier says, okay, well, I'm actually interested in the input restricted to this particular coordinate, this first coordinate. And then in the second round, they say, and actually, I'm interested in it restricted to that first coordinate and that second coordinate. So you can think of it as sort of incrementally specifying a particular coordinate until in the final round, the verifier has specified exactly the coordinate that they're interested in, and they're forcing the prover to make a claim about the evaluation of their function at that coordinate. And then the reason that all this works as a way of sort of checking the correctness is that in each round, you can relate the claim made in the previous round to the claim made in the current round and check consistency. Okay. So I haven't gone too deep into technical details, but sort of this is the general idea that you're sort of the prover makes an initial claim about the whole input, which gives you the answer that you want, and then you progressively tie that claim to more and more specific claims until it becomes a claim about something that you've previously used to check. You can then use to check the correctness because of requirements on consistency. Okay. So this is very nice because all the costs before that were polynomial now become logarithmic or polylogarithmic. And it's actually fairly cheap to do this calculation. So far this sort of looks like a nice exercise in theory because I've shown you lots of confusing looking polynomials and I've talked about some fairly specific functions that look somewhat disjoint from what one would ever actually want to do. So let me sort of say how these ideas then can be made sort of more general and more practical. So in general, you'd like to not just look at particular computations, but look at sort of more general computation functions. And actually, there's a nice framework laid out in a stock paper by Goldwasser, Kallai, and Rothblum that sort of sets up a framework that we can then instantiate with these ideas. So what goes on here, what goes on in sort of this setting, is it says, well, let's look at general class computations, those that we can sort of model naturally as arithmetic circuits. So these are sort of circuits in the traditional sense of circuits, but where the gates are arithmetic operations, so say addition and multiplication. And how are we going to use this kind of technology? Essentially what we do is we start with the prover, prover claiming a value for the output of this circuit, and then we're going to successively reduce this claim about the output of the circuit to a claim about properties of the circuit at each successive level until we get from the output of the circuit to the input level of the circuit, at which time the prover is making a claim about a low degree extension of the input at some random value, which is exactly where the verifier has evaluated the input extended to that random value. And again, sort of using successive agreement checks between each iteration, each round, to enforce global consistency. Right, so picture sort of showing the same thing. We want to think of the circuit as essentially being layered. We have an output layer, an input layer, and some intermediate computation layers. We want to reduce a claim about the output layer into a claim about the input layer using these kind of polynomial low-degree extension evaluations to enforce consistency between each step. So there's a lot of sort of engineering details involved in actually putting this all into practice. I'll sort of skip over some of the details in terms of what goes on here. One major issue is just that we don't want, naively implementing this kind of thing forces the verifier to sort of compute functions over polynomials that define properties of the circuit. And actually, if you sort of directly iterate over those, then you're effectively iterating over all the gates and wires in the circuit, and so it's not clear that you do anything better than just directly evaluating the circuit. So where you can really win here is the fact that most computations are not arbitrary, but they're very structured, and that when the wiring of the circuit has a significant structure to it, then you can more effectively do these computations and compute the contribution of sort of the gates all at once rather than one by one. So let's actually show some numbers. Here's what happens when, in some work with Justin, where Justin Taylor sort of went off and implemented all of this. And what it shows is that, so what are we seeing here? We're seeing a couple of different problems in this setting. One, a fairly standard one, computing the second frequency moment. That's fairly straightforward. Second one, looking at F0, that's the number of distinct items. That turns out to be much more complex. And uses essentially some various tricks with encoding that as in an arithmetic circuit. And lastly, a pattern matching problem that sort of says, imagine your input as being a large string, your query is to find occurrences of a particular pattern in that string. And what this shows is that using either sort of standard addition and multiplication gates or sort of throwing in a couple of extra gates, then we can do this reasonably efficiently. Certainly the communication size is very small. We're talking about kilobytes of communication. The number of rounds is moderate, talking about hundreds or thousands of rounds. The time for the verifier to do their check is almost nothing, effectively at the limit of what we can measure in terms of timing. And the time of the prover is tolerable, right? So these instances are not huge by any measurement, but it's saying that at least this idea is sort of on its way to practicality, that in sort of hundreds of seconds of effort on the prover, we can verify these computations. So let me just sort of wrap up by saying sort of where this work has been going in the last year or two, how we can sort of further attack various of these costs. So one observation is that in building these kind of provers, so the main bottleneck in this work is engineering an efficient prover, engineering a prover whose effort is not so much substantially worse than the cost of doing the computation itself. So one observation is that the prover's work in all of this is actually quite data parallel. For the same reasons that the verifier's work is a linear function of the input, the prover's work is sort of parallel over the data. So you can parallelize, in particular, you can take advantage of things like GPU for acceleration. So Justin and others had a hot cloud paper on this last year and showed the kind of expected tens to hundreds of times speed up by shifting the work onto the GPU. Most recently, Justin has a nice set of results in crypto coming up soon that basically says, with more engineering, with more careful choice of how you define these polynomials that are being evaluated, you can reduce the effort of the prover by allowing them to sort of recycle more work, and that actually saves you a log factor. And you go, well, what's the log factor? Well, these are moderately large domains, so a log factor is tens. So in particular, when you implement this stuff, it shaves off factors of 100. So again, you're sort of going from these prover times of hundreds of seconds down to provers of time for the prover in the realm of single-digit seconds. Most recently with Amit and Justin, we've been looking at sort of other variations of this problem. So ideas around when you have this, when you have data drawn from an immensely large possible domain, say the sort of domain of all possible pairs of IPv6 addresses, then within that huge domain, your data is relatively sparse. So the results that we have, that I talked about so far, have dependency on polynomials in the size of the domain. And what we'd like to do is actually reduce that to being polynomials in the size of the sort of the true sparsity of the data. It turns out you can do that. It introduces some additional problems in sort of checking the correctness, but you can take those results in terms of cost that scales with the size of the domain and turn them into cost that scales with the size of the support set of the data. And there are many variations. Lots of other people are looking at these kind of questions from a more crypto perspective. So some recent work coming up in SIGMOD this year, we're looking at using cryptographic tools to generalize this from a sort of a two-party model of a prover and verifier into a three-party model where you have a data owner, the server that's doing all the work, and then possibly untrusted clients who are trying to actually find answers to things. So I think I've probably exhausted the time available, so let me sort of just leave this slide talking about open questions up there and stop there. Thank you.